Hello everyone. Today we are going to discuss on how we arrive at the Navier-Stokes equations that we have seen before from the fluid mechanics courses. And in a way, this is a recap, a refresh session from the fluid mechanics courses where we are going to see in details how the momentum and also the continuity equations are being used to get to the Euler and also the Navier-Stokes equations. Okay, so we are here now, and hopefully we can cover all the elements under the fluid flow equations, which basically will focus on the continuity and the momentum equations that we are going to focus for the Navier-Stokes equations. Okay, we are not going to focus the energy equations for this course. So this is the equations of the Navier-Stokes that we have seen so much in our course and also from the previous courses that you have taken. Okay, so what the terms refer to. Okay, I've shown this. I've shown on this screen. So the first one refers to the unsteady term. Okay, dv over dt. V here refers to the variables, the velocity. So over dt, change over time. So that's the unsteady term. The second term here, this is the convective acceleration or the movement within the vector field. And on the right side, okay, we have the terms over here. Okay, this basically based on the assumptions of a Newtonian fluid. Okay, this is for the viscous diffusion term. Okay, to arrive to these equations, several assumptions needs to be done. So one of them is the use of Newtonian fluid in this derivation. So we are going to look later how these assumptions help to achieve or to arrive at this equation. And the last term over here, this is the dynamic pressure. Okay. Now, as I said, among the assumptions that we make, the first one is we use a Newtonian fluid in deriving these equations. And the second one, we assume that the density of the fluid is constant, means that there is no compressibility or incompressible fluid. All right. If you look into more details, okay, what the terms refer to, the terms here in the first red box here, okay, this refers to the non-linearity of the equations, okay, which is the source of most problem. Okay, all right. So why is it non-linear? Because you can see that you have the velocity component, you have two times. Okay, you have two velocity components multiply by another velocity component, which induce the non-linearity form. Okay, and this is the most complex or the difficult part of the equation. And the second one is the second order term. So what we are going to look in our course, in our study, basically for the Navier-Stokes equations, we are going to deal with the second order term. Okay, so what does a second order term means? Okay, hopefully we're going to cover that in this session. Okay, but basically you need to understand that why we need CFD to solve the Navier-Stokes equations, because once we derive these equations before we reach to this final form, to this vector form of the Navier-Stokes equation, several assumptions need to be made, and we are going to be left with several unknowns, and the unknowns, okay, can only be solved by using numerical modeling, okay, because we have no linearity over here, and we have a second order term. Okay, the second order terms refers to the higher accuracy of the model, okay, where we can get a better approximation of the flow field. Another assumptions that we can make along the way is that the fluid is inviscid, means that the viscosity of the fluid can be assumed to be zero. Okay, so when that happens, what we're going to get is we can remove the viscous form, which is this part here. Okay, viscosity is mu, so the term will cancel out. So we are going to left with the unsteady term on the left. Okay, and this part over here, the non-linearity is still there. Okay, but we are left with basically we can cancel out the viscous term to get this equation that is called Euler. Okay, so when we go back and we look again over the semesters, we keep on asking what is CFD. We understand that CFD basically just a tool or a means to analyze a fluid system, okay, by using numerical modeling to get a solution. Okay? So we understand that we can simulate pretty much everything, but uh, to understand that why we need to use CFD, so that's why we need to cover this part here. Okay. So it mentions over here we use CFD as a mean or as a tool to get a solution. But what is solution? What is defined as solution? Okay. So the solution is basically to give us the fluid's velocity field or the vector field. So we understand hopefully by now in a fluid, for example, okay, we have three components of velocity, which in this case is the I, J, and K. Okay, so there are three dimensions. The components are in three-dimensional flow. So the solution means we want to solve the fluid's velocity field. We want to get at each direction x, y, and z, okay, or the components I, J, and K. What are the properties of the fluid? Okay, so aside from the fluid, we also want to get the associated the pressure field. Okay, it's not just the velocity. We also are interested in the pressure field, the energy field, for example, if you are dealing with a change of temperature, for example. Okay, and so the equations above is only for the Navier-Stokes equation, the one that we looked before. Okay, for a more complex situation, we can also integrate or include in the Navier-Stokes equation or couple together to solve some uh, other problems such as heat transfer equations or chemistry, or we want to look at the reactions involved in the uh, some mixture, for example. So we can use the Navier-Stokes, okay, along with other equations, related equations, to get or to solve a more complex problem. Okay, so just remember the one that we looked just now is just for the Navier-Stokes equations. But if you want to solve, okay, Navier-Stokes is basically for fluid. So anything related to fluid problems, we can use the Navier-Stokes. Aside from that, if you want to simulate, for example, fire, we discussed this in the previous class. If you have, or if you want to simulate fire, the behavior of a fire, okay, so the Navier-Stokes equation alone is not enough. Okay, fire, yes, it can be simulated. Fire is a type of fluid, can be assumed as a type of fluid, but it cannot be solved or simulated just by using the Navier-Stokes equation. So for fire, for example, we need, for example, Navier-Stokes equations as well as the energy equations, okay, plus the heat transfer equations. Okay. So now we have to couple another equations along with the Navier-Stokes to solve for that particular problem. Okay, so that's just to show how powerful the equations are. Basically, the Navier-Stokes just solely or exclusively, specifically for the fluid flow. Okay. Okay. Other than that, we need to couple them together. All right. Just a bit of highlight over here. So this is taken from the textbook. So what we are going to cover in this session is basically how do we start? Basically, how do we achieve the final equations of the Navier-Stokes? Okay, how do we get the second order form, or how do we get the non-linearity in our equations? So to do that, we need to understand, we need to start somewhere. Okay, and everything, okay, as we discussed in the class, in CFD, for example, they are governed by the fundamental governing equations of fluid dynamics. Okay, so over here, everything in CFD is governed by the fundamental equations of the fluid dynamics. Okay, in this case, the fundamental equations are the continuity equations, the momentum equation, and the energy equations. Okay, what does this equation refer to, or basically represents, is the principle of which the mass is conserved, number one, the Newton's second law, which is momentum equation, F equals to ma, and finally, the energy conservation. So they are all depends or derived from these three fundamentals. Okay, and some students might ask, okay, so I know how to use this software already. So why do we need to know the derivation of the Navier-Stokes or the Euler equation? Okay, the reason is simple. I think this author, in the textbook, the author has done a, a, a very good job in explaining step by step, okay, why we need to understand the behavior or the working principle behind the software, behind the GUI, graphical user interface, before we can uh, proceed to simulating whatever work or whatever problems that we have. Okay, first is because we want the students to be very comfortable with the equations. Okay, before you continue with your study. Okay. So do not be afraid. So some of you might see second order or the non-linearity form. You get kind of nervous. It all, remember, everything in engineering can usually or mostly can be tied back to the mathematical formulations. Okay, we can pretty much solve everything with mathematics. Okay, so you have learned this in calculus, you have learned this in fluid mechanics, so it's just a revision. Okay, and more importantly, okay, first to familiarize yourself. More importantly is the part over here. If we do not understand the meaning or the significance of the equations, okay, of these equations that we are going to look at, then how can you be confident, or how can you be assured of the output that you produce in your work, in your CFD work? Okay, I keep on saying this. If you have a black box, okay, remember we covered this, you can put any value and there will be some value out. But the question is how to check your output. This is the question. So without the fundamental understanding of the working principle behind the software, I think you are kind of like a blind people. You are trying to do something that you know you can do, but you are not sure what it is. Okay. All right. So the black box, we have looked at the description. What is a black box before, right? So when we start with the fundamental physical principle over here, okay, so let me highlight this. So we are going to look at how the mass, the conservation of mass, the Newton's second law, and the energy conservation can be basically tied back or can be related if you follow the lines here. Okay, they are all going back into the equations that we are quite familiar with from the fluid mechanics. Okay, the governing equations. So the mass conservation is related to the continuity equation. The Newton's second law is related to the momentum equation, and energy conservation is energy equation. Okay, so we're going to look into that. Aside from that, we have several models of the flow that we can use in deriving the Navier-Stokes and Euler equations. Okay, among them, we have fixed finite control volume. We have moving finite control volume, fixed infinitesimal small volume, and also the moving infinitesimal small volume, okay, or the moving flow elements, okay. We're going to look this in brief, okay, what does it mean and how it can be used to solve the equations that we want, okay. So, but in principle, all students just need to understand this is what matters, okay. We understand continuity equation, momentum equation, the energy equations a bit, and that's the driving force behind the CFD tools. Okay. All right. So we covered this before. All right. So this is from fluid mechanics. Okay. There are basically four models that we can look at. So if we look from the first one in A, okay. So we have an element, the fluid element, okay, which is defined as a control volume here. Okay, let's give it a color. Okay, set the fluid element. So now the element is assumed as a finite control volume that is fixed in space, meaning that it is not moving. Okay, the only thing that is moving is the fluid around it. Okay, so that's the first assumptions. Okay, so we have fluid moving around the elements, but the element itself, the control volume, is fixed in the space. The second model that we can use, okay, under A, so again, we have a control volume, but now the control volume is moving along with the fluid. Okay, so it's moving along with the fluid. So instead of stationary, now it is riding along with the flow. Okay, so that's the first two. The second model in B, okay, we have infinitesimal fluid element. Okay, just to recap, infinitesimal means very, very small. A very small fluid element fixed in space with the fluid moving through it. Okay, so the difference between A and B, the first one we have a control volume. Okay, means that there is a volume, a quite large volume. Finite means there is a substantial amount of volume. Second one for B, infinitesimal means we have a very small volume, part of the element. Okay, we just focus on the very small element of the volume. Okay, so for the second one, the uh, volume again is fixed in the space and the flow is moving around it. And for the second models, the small element is moving along with the uh, flow. Okay, so we are going to use the control volume assumptions and also the infinitesimal fluid element assumptions to derive the continuity equations and the momentum equations. Okay. So just to recap again, um, what does this mean? Basically, we have a surface, S is the surface. So ds is basically a vector elements for the surface area. Okay. Um, the mass flow rate is given as rho AV. Okay, this is a recap from fluid. And what we have over here is basically if we look at the element, if it is moving along the fluid, so we have in terms of the ijk components. Okay, so I basically is x, k is z, and j is for the y. Okay, all right. Okay, and then in fluids, we cannot run away from these two terms, Langarian and also Eulerian. Okay, uh, so I think it helps to understand what the concept is about. So Langarian means we follow arbitrary amount of fluid particle to simulate the whole flow. Okay, meaning that, okay, the examples given here, oops, sorry. Okay, for the Langarian concept, let's say this is a missile. We have a missile. So now, if we use the concept of Langarian, we are going to look at the observer that is fixed to the missile, meaning that if we want to follow the missile, we assume or we the position of the observer will move along with the missile. Okay, so let's say this is position A naught, original position. This is A1. That's okay. If time, this is T naught, time original or zero time. This is the time after it moved. Okay. So Lagrangian means the observer will be fixed to the missile. For the Eulerian, okay, however, the observer is fixed on the ground, meaning that it is observing the missile, okay, based on the I, J, and K components, meaning that it follows the missile, okay, by using or referring to the components or to the positions of the missile in the fluid. So, for example, in Illyrian, okay, the observer will observe arbitrary amount of fluid particles to simulate the whole flow. Okay, all right. Okay, so let's start with the first one. Something that we have, I think, covered this along the 4-year course in Unimap. For example, the first one, continuity equations. What is continuity equations? Basically, the principle is the mass is conserved or conservation of mass. Okay, and to get to the continuity equations, how the continuity equations is derived, we are going to analyze this by using the model of the finite control volume fixed in space. Remember the 4 models that we looked before? Okay, so we are going to use the first model, okay, where we have a control volume here that is fixed in space, and the flow, the fluid is basically passing through the control volume. Okay. What does it mean by the mass is conserved? In the simplest term, it means the net mass flow out of control volume through surface S, okay, the S is the control surface, is the same as time rate of decrease of mass inside control volume. Okay, all right. Okay, so we understand that conservation of mass basically means mass is conserved. For a system, okay, we can write down the d over dt of the mass in the system is equals to 0. Okay, means that the change with respect to time of the mass in the system is equal to 0. So that's the first one. And for a control volume, okay, it can be written as the following. The partial derivative d over dt, okay, is an integration of the summation of the control volumes. Integration is basically summation of the whole control volume, okay, of the rho dv. So rho dv, remember, is the mass, okay, and plus the integral of the control volume of rho v dA. So this is the v dot n is the dot product. Okay, so v is the velocity, dot product n. So n is the dot product of the outward normal. Okay, so we have for the control volume, the first one here is the rate of change of the mass in control volume, okay, over time, d over dt, change of rate. And for the second term, this is the net rate of flow of mass across the control surface. Okay, so the first term, okay, basically is the unsteady term, and the second term is the flux term. Okay, the unsteady term because we are dealing with time, dt, and for the flux, okay, because we are dealing with the outward normal, the velocity in the outward normal. Okay, so dA is just the differential area. Okay, all right. Okay, so this just again just a description or elaboration on what is the dot product. Okay, we learned this back in calculus. So we have N is referred basically the unit vector, which is perpendicular or 90 degrees to the surface of the ds, surface area. Okay. So over in the derivation, in deriving the continuity equation, momentum equations, you will notice that we are going to use two type of differential term. The first one is this. Okay. When you say something like this, d over dt, for example, this refers to the partial derivative. Okay. And when you see another term, okay, d or d like this is the differential term. So there is a difference, okay? Either this one or this one is different than d or d like this, okay? So please take note, okay? The first one is the partial derivative, and the second one is the differential analysis. Okay? So this is from the calculus. All right. So when you look at the differential term for the first one, differential form, excuse me, differential form for the first term. Okay. So when we have d over dt integration of the control volume for rho dv, we can equate this to be d rho over dt, okay, multiplied by dx, dy, and dz, and this is the differential of volume. Okay, and we assume that the density is uniform in the dV, differential volume, okay, because we have a very, very small element. And for the second term, we are dealing with the rate of mass, and now we are just going to focus in just the x direction component, okay? All right, so imagine that we have the element, say, given here. Okay, so this is our element, okay, in this cube over here. All right, so the element, okay, if we label them, so this is our dx, and this is dy over here, and of course we have dz. Okay, so just remember our orientation from before. We have this is x, z, and y, which correspond to I, this is k, and this is j components. Okay, so from here, if we look at the the surface on the right side over here, okay, and if we look at the uh, component of the mass flow rate, okay, so in this case, the component of the mass flow rate, okay, is given as the rho u, okay, so the density mass component of the mass flow rate can be simplified as a density in the u direction, so density multiplied by u, okay, for the x component of the mass flow rate. Okay, so what we are going to have is we are going to get for the right side over here, okay, assuming that the flow or the fluid basically passes through this element on the right side as out. So we have rho u plus d over dx, the partial derivative of the rho u over here, okay, multiplied by the dx over 2. So dx over 2 here refers to the distance from the center of the element. So at the center of the element, we are going to have the density, okay, that dot over here. Okay, so in the middle of the element, the density is in the middle. So if we want to get the movement or the component of the velocity towards the right surface, okay, which is going out of the element, so we are going to get dx over d2. Okay, we have plus sign over here because it's moving to the right direction. And we multiply them with dy over dx because this is the area. Okay, how we get this term? This is by using the Taylor series expansion for the quantity of rho u, okay, which is the flux term. Okay, similarly, if we look on the left side over here, okay, where the flow is coming into the element, okay, in. So again, if you write the similar component, you're going to get rho u, that's the x component of the mass flow rate, we have minus term over here. We have minus term over here, okay, because it is moving to the left. Okay, so we assume that the density is located or is positioned in the middle of the element. So since it is to the left of the velocity density position, so we have minus d over dx rho u, the density in the x component, multiplied by dx over d2. Okay, remember, because the position here is half of the dx element, and we multiply again by dy dz for our area. Okay, and now, so the net rate of flow, or sorry, the net rate of mass outflow in x, okay, can be written as here. X equals to dx multiplied by rho u dx dy dz. Okay, so this, if you basically subtract the right side to the left side, okay, you are going to get the x component here of the mass of the outflow, the net rate. Okay, net, remember, net. So basically you subtract the right equation to the left one. Okay, so similarly, for y directions, okay, if you do the same thing, okay, you are going to get d over dy rho v. Okay, remember, u here is for the x component, the x velocity component. V is for the y velocity component, and W is for the z velocity component. Okay, so for y, you're going to get d over dy of the rho v dx dy dz, and for the z direction, you have d over dz, the partial derivative of the rho w, okay, the z component, multiplied by dx, dy, and dz. So now, if you add them up together, you'll get dp over dt plus, okay, this one, plus d over dx rho u plus d over dy rho v plus d over dz rho w, which is equals to 0. Okay, now from here, if you notice, the dx, dy, and dz term, okay, can be cancelled out or crossed out because we can equate them equals to 0. So if we rewrite this equation here in the vector notation, we can get the partial derivative of the rho in respect to the time, dp over dt, plus this symbol, that's the vector notation, multiplied by rho v equals to 0. And this is our continuity equation. Okay. All right. So that's how we arrive at the continuity equations. Okay. If you go back quickly, okay, we have two terms. The first one is the unsteady term, d over dt here, the first term, and the second term is the rate of flow mass. So if we derive each of them, and we substitute what we have from the rate of mass into the equations, basically we go back over here. Okay, so 1 plus 2, the first term, okay, plus the second term. Okay, from the derivation that we get, that's how we arrive at the vector notation of these continuity equations. Okay, so quickly, some notes before we proceed. Okay, what does this term means? Okay, so this is just a vector operation. Okay, so this symbol, the vector operation multiplied by the v here, this is the vector operator for ijk. So if you look over here, the one that we have here, the vector notations. Okay, so these vector notations basically, or the vector operator, basically refers to the I, J, K, or the components of the partial derivative of each of them. So d over dx, d over dy, and d over dz. So that's how we can write our continuous equations such as this. Because remember over here, we have d over dx, we have d over dy, and d over dz, okay, which can be simplified as the vector operator, okay? And the v here, of course, refers to the velocity component, okay? All right. Okay, so just a recap. Okay, by now we should understand the difference between partial derivative and the substantial derivative, which is used in the textbook. Okay, it's not the same. Similarly, we have a differential term. Okay, the one that we have over here, okay, which is not the same as I showed before. D over, for example, dt is not the same as d over dt. Okay, so partial derivative and the differential derivative are two different things. Okay, so now we move into the momentum equation. So in this part, we are going to apply another fundamental physical principle to a model of the flow, okay, which is F equals to ma, which is the Newton's law. And to do that, we are going to analyze by using the moving fluid element. So remember, previously we assumed our control volume to be fixed in the flow field. But now our control volume is moving with the flow. Okay, so different models. All right. So to start with the conservation of momentum, okay, we look at the system as a whole. So we have F, the vector F equals to d over dt, okay, and integration of the system v dm. Okay, so this is the change of momentum in the system. And for the control volume, okay, this is by using the Reynolds transport theorem to write over the conservation of momentum in integral form. Okay? So for the control volume, we are going to have the summation of the forces in the control volume, which is equals to d over dt integral of the CV, v multiplied by the rho dv differential volume. Okay, this refers to the momentum part. Okay, and remember, whenever we have a dt, this is the unsteady term, and we add them, okay, we add the equation with the integral of the control surface, v as v, and dot product of the outward normal, n, multiplied by the dA, and this is the flux term. Okay, so by looking at the infinitesimal fluid mass, okay, we use dm, okay, so differential mass. So we can get df equals to d over dt multiplied by the vdm. Okay, so dm here is the element of the mass, okay, which is equals to dm multiplied by dv dt. Okay, so if you look over here, this is quite familiar. Okay, this is basically the acceleration. Okay, so when we get the df, which is equals to dm multiplied by a, the acceleration, so that's the form that we are quite familiar with, which is the momentum. Okay, F equals to ma. Okay, for fluids mechanics, there are several types of forces acting on the fluid elements. So for the one that we're looking at, okay, there are two forces that are relevant that we need to understand. The first one is the body forces, which is the weight of the element. Okay, and the second one is the surface forces, okay, which is normal and tangential to the element, the fluid element. Okay, for the body forces, I think it's quite straightforward. So for the differential force, for dFb, B refers to the body. We have equals to dm multiplied by the g. G here refers to the gravity. So F equals to ma. A here refers to the gravity acceleration. Okay. And now we are going to look at how we can get the surface forces. Okay, remember the surface forces in this case, we want to look at all the forces acting on the surface of the element. Okay, so before we proceed, just a recap. There are two different forces that we need to understand. The first one is the shear stress, okay, given usually by tau. Tau is a shear variable. So it relates to the shearing or deformation over time. Okay, so if you move the fluid, basically, what is going to happen on the surface, for example, you are going to get shearing. So this is from the original position. When shearing happens, it's going to move to this particular direction of the force, okay, where the force is acting. Okay, so this is a new position. So shear causes deformation over time. The other one is the normal stress. Okay, I just want to highlight over here, uh, in some literature, in some textbook, okay, they are using the same notation for both stress and also shear. Okay, sometimes they use, for example, over here, this is tau xy. Okay, sometimes the normal stress, the literature will also use the same term, normal stress tau. Okay, but the difference is in terms of the subscript over here, how it is used. So for stress, it must be the same like this. In some literature, however, okay, they want to differentiate between the shear stress and the normal stress. So they use a different notation, okay, which is the stress symbol, okay, sigma. So they use sigma as x, okay. But not to be confused, as long as you understand the superscript here is the one that is important, okay. But just keep in mind, sometimes you are going to see normal stress is being used as tau as well, but most of the time the literature, sometimes they want to differentiate between the shear tau with the normal sigma. Okay, so for the sigma, okay, it relates to the change of volume. Okay, it's not shearing, so it is normal to the elements. Okay, so it involves the change in volume. So that's the difference between shear and stress. All right. Now, if we consider an element in the area of the fluid, okay, let's say dA. So dA is the element in the area, element in the area of the fluid. Okay, we have a very small one, dA over here. So we are going to have the following forces. We are going to have three components, three different forces acting on the surface. The first one is the dFn. Okay, the Fn is basically normal. The normal force to the dA. Okay, normal means is perpendicular. And then we are going to have two other forces, which is F1 and F2. And this is tangent to dA. Okay, and this here is basically the shear force. So this is the normal force, N is normal, and F1 and F2, it is tangential to the dA. And for the normal stress, okay, sigma N, okay, if the limit of the dA approaches 0, okay, we can write down as dFn divided by dA. Okay, remember, we have stress equals to force divided by area. So now we are talking in terms of the differential area. So for shear stresses, tau 1, okay, when the limit of dA approaches 0 means is very small, we can get dF1 divided by dA. Similarly, for for shear for tau 2, okay, when the limit of dA approaches 0, we can get dF2 divided by dA. And with reference to the coordinate system, okay, we are going to use the following system, x, z, and y, such as this. Okay, when we look at the first one here, let me highlight this. Okay, just on one surface of the element. Okay, so the normal force, okay, or the normal stress is sigma xx, which is the normal stress, and the tau xy and tau xz, okay, the one that is given here, xy and xz, is the shear stress on that particular surface. So remember, for every surface, you are going to get three different forces, normal force and two shearing forces. And just to highlight again, the subscript notation, okay, meaning that how do you get xx over here? How do you get xy or xz? So the notation, okay, the first refers to the direction of the normal vector. So if you look over here, because we are looking in terms of the x direction, okay, remember x to this side. So when the normal force, okay, is goes to the right direction, so we have x here because it refers to the direction of the normal vector. And the second one refers to the direction of the stress vector, meaning that, for example, if we have tau xz over here, x, the first one, let me write over here, tau x, because it is located on the surface where the normal stress is moving in the x direction. So they are sharing the same element. So the first, the stress component or the normal stress component is moving or heading to the x direction. So the first term is x, and the second term refers to the direction of the shearing force. In this case, it's moving to the z direction. Okay, it's moving towards us. So that's why you get tau xz. Okay, similarly, for tau xy, okay, sorry, it should be x. Tau x, the first one, because it is sharing the same element where the normal stress is moving in the x direction. And the second one, y, because it is moving towards the y direction. Okay, so that's the subscript notation. Okay, so before we proceed, let's look at the sign convention, right? So now assuming that we can cut the element into two, okay, if we cut it to two, okay, so if you look up from the right element, okay, anything that goes to the right of x is positive, and anything that is going towards z direction is positive. So this is positive z, this is positive x, and anything moving up is positive y. Okay, so basically this is positive, positive, positive. Okay, so if we have another axis over here, okay, if I use a different color, okay, remember this is z, y, and this is x. Okay, on the left side, remember, there will always be the same magnitude but opposite direction forces, okay, from the Newton's law. So for the left side, for tau xy, okay, is moving down. So that's negative. So negative for tau xy going down. And then we have tau xz, okay, towards the back. Okay, this is negative tau xz. And finally, we have sigma xx to the left. So sigma xx is negative because it's moving to the left. Okay, so that's the sign convention. Please note, in some literature, they do not include pressure P in the analysis because they want to simplify. They just want to focus on the body forces. Okay, but if I'm not mistaken, can I just go quickly to one diagram that I have over here? Yes. So if you look at the details of this diagram, for example, okay, in this literature, in this textbook, for example, the pressure term is included in the analysis. Okay, but for our case, we are going to look at the derivation of the body forces only, and the P term, the pressure term, will be included once we add up all the terms together. Okay, just for the sake of simplifying our derivation. Okay, so the P term here, they should be there, but we are going to keep that out for now. Okay. All right. So for surface forces in terms of all the stresses, okay, now remember we are going to look at the stresses only in the x direction for all the surfaces. Okay. All right. So let's look at the first one. Okay, for dx, remember for dx, this is the direction. Okay, and this is dz and dy. Okay, remember from the center, that's the origin of the element. Okay, if we have to the right over here, we can write down as sigma xx plus dx of d over dx of sigma xx multiplied by d over x, dx over 2, sorry. So dx over 2 is basically the location to the right here from the center. Okay, multiplied by dy dz. This is the area. Okay, so this is quite similar to what we have before. And to the left, we have dxx minus, okay, minus because we are moving to the left. Remember the sign notation of d over dx of sigma xx, the stress term, multiplied by dx over 2. This is, excuse me. Okay, so this is dx over 2, dx over 2, and multiplied by dy dx, that the area. Okay, so that's for the surface over here. Okay, the direction that we have. Now, next, when we want to look at the front surface of the fluid element, okay, which is in this case here, okay, front and at the back. Just now, just for the sides, okay. For the front, we can get on the right side, okay, the right arrow here, we have tau zx minus d over dz tau zx dz over d2. Remember dz over d2 because it is in the middle. Okay, so we have dz over d2 and multiplied by the area dx dy. And similarly, for the front face, this is for the back. I'm sorry, it's not the front face. This should be at the back. This should be at the back. So meaning that here. So for the front of the element, we have tau zx and plus, okay, because we are moving to the right direction. This is to the left direction, so that's why we get negative. Okay, so we have the following terms, dx dy, and finally, when we look at for the top and the bottom of the element, okay, this is top, bottom. Top, remember, the sign convention means positive. Bottom sign convention is negative, so we have positive for the top and negative for the bottom, okay, with the following notation. Okay, all right. Okay, so from there, what we can write is we group all the forces in the same direction together. Okay, so conservation of momentum, we group all of them together. So for x, okay, in the I, j, and k components. So for I, x component, we have d fsx, okay, stress force in the x direction. We have d over dx sigma xx plus d over dy tau yx, okay, plus d over dz tau zx, okay, multiplied by the elements, the differential volume. Okay, so this is for x. Okay, all the terms on the x direction, we group them together. Okay, so how just to recap, okay, how we get this, we have tau xx because tau xx is moving on the right direction, and then we have tau yx, tau yx, tau yx because it's moving to the x direction. Okay, remember this is 1, 2. This is numbers. Let's say number 1, number 2, 1, 2. And finally, tau Zx. Okay, tau Zx because it is moving in the right direction. Okay, all the stresses that are moving in the same direction, in this case x, okay, we group them together. And similarly, if you do for the j and k component or for the y and z component, you are going to get the following equations. Okay, and okay, so this is just a recap. The equations of motion, how we get the momentum Fx equals to max. Okay, how we can derive, we can get du over dt for the area, and the mass itself is in this following form, which we are going to use in substitution later. Okay, so for Fx, we can write down as the following, which is density multiplied by the components of u. Okay, as the following, this is du over dt, u, okay, in terms of du dx, v du dy, and w du dz. This is for x components only. Okay, please keep in mind. Okay, so for the conservation of momentum, if we substitute everything that we have, okay, from before, if you look at before, we have df, which is equals to dm multiplied by a, the acceleration, and we have dm, which is given by the following notation. Okay, so the full term or the full equations of motion can be written as follows. We have the body force rho gx. Remember, this is only for the x direction. And then we have d over the x stress term, or this normal stress, sigma xx, plus d over dy tau yx plus d over dz tau zx. And these are all the surface forces in the x direction. Okay, which is equals to rho multiplied by du dt. This is F equals to max. Okay, du dt plus u du dx plus v dy this is du dy, and w du dz. Okay, for x component. Okay, so if you write for all of them, okay, for x component, y component, and z component, okay, you are going to get something like this. Okay, and for all of this, okay, remember just now, in the initial step, we did not include the gravity or force, okay, but now we include all of them. Okay, so from here, we have three equations, okay, plus continuity equations, which is equal to 4 equations with the following unknowns. We don't know u, v, or w, and also all the stresses. We have no idea what they are. Okay, now, if we look at for one more thing, if we assume our flow to be inviscid, okay, inviscid means there is no viscosity. Okay, when there is no viscosity, it means that there is no shearing stresses. Okay, when that happens, you can cross out all the viscous term. You are going to get the following equations, okay, which states that the normal stress sigma xx, which is equals to the sigma yy equals to sigma zz, will be equals to the negative p. Negative p here refers to the pressure. Remember, there is a pressure acting on all sides of the element. Okay, but previously we did not include in our derivation. But just remember, in all of the directions, we have pressure acting on the elements of the fluid. But now, when there is no shear stress, because the viscosity is assumed to be zero, so there is no shearing. So we are only left with the sigma xx, for example, over here, okay, and sigma xx, which is equal to sigma yy equals to sigma zz equals to negative p, because the pressure will always be acting on the opposite direction, acting on the fluid. Okay, so this is happens when we assume inviscid flow. Okay, let's not put here. Okay, so this is the details. Basically, if we include all the forces on the element. Okay, remember this is infinitesimally small element, very, very small element. And these are all the forces. The normal forces, okay, remember, as I said before, in some literature, they use tau xx for the normal or the sigma xx, okay, but it's just the same. So they use tau xx, which is the same as sigma xx. So these are all the elements acting on the, all the forces acting on the fluid elements. Okay, we have pressure, don't forget. Okay, and aside from the surface forces, which usually we have shear and normal, we also have body forces, which is the gravity. Okay, all right. So from all there, from all the derivations of the momentum equations before, okay. So from here, we can write down the following terms. Okay, this is what we have before. So for the x direction, so this is the term that we get for x component. Okay, the rho jx refers to the body force. Okay, this side here, this is the surface forces. Okay, this is normal, and this two is for the shear forces. And the right side is based on our derivation from the F equals to max. Okay, now if we look over here, we can write down Euler equations. Okay, the Euler equations basically means there will be no viscous term. Okay, so when there is no viscous term, meaning that it is inviscid, so tau equals to 0, and meaning that, okay, which basically means inviscid flow. There's no shearing. Okay, tau equals to 0. So when you cross out tau, okay, in our equations, you will be left with the Euler equations, which can be simplified as follow. So you have the body force, rho gx, multiplied by the dp over dx. Remember, this is the pressure acting on the opposite direction. This one, we did not include the pressure yet. No pressure yet. Okay, but the full equations of the Navier-Stokes and the Euler must include the pressure. So we have body force, we have pressure force, okay, equals to rho multiplied by these terms over here. Okay, remember now we no longer have the viscous term because the shear stress is equal to 0 for Euler assumptions. Euler equations, we neglect tau because it is inviscid. Okay, so if we convert this into vector notation, rho g, okay, rho g, this is the general form, rho g minus the vector operator p. Remember, this basically means d over dx, or any value, dx or d over dy or d over dz. Okay, the vector operator, which is equals to rho multiplied by, okay, remember we have over here d over dt, okay, unsteady term multiplied by v. V here refers to the velocity component uvw, okay, and plus v dot the vector operator. V here refers to the velocity uvw multiplied by the vector operator, which in this case this part, okay, d over dx, dy, dz, and multiplied by v, okay, velocity again. So which is what you have u v w over here on the outside. Okay, so that's how you arrive at the Euler equations. Okay, so hopefully now you understand a bit basically how the Euler equations with the assumption used inviscid, for example, and how the vector notation or the final form of Euler and Navier-Stokes are written. Okay, so this is for Euler. We are going to continue with the Navier-Stokes derivation, which is just a bit more and show and look at how different the Navier-Stokes equations with the Euler assumptions. Okay, so all right, so let's look at the Navier-Stokes derivation next. Okay, so we look at how the Euler equations are derived. Okay, basically how we arrive at this vector notation for the Euler equations. Okay, just to recap again, for Euler, remember that we assume the flow to be inviscid. Okay, what does it mean? The viscous property equals to 0, no viscosity, which in terms give tau to be equals to 0. Tau is the shear stress. Okay, when there is no viscosity, the shear is 0. So we can cancel out the shear term, the shear stresses in the derivation that we get before to get the vector notations here. All right. So to proceed from Euler to Navier-Stokes, basically one might ask, okay, what is the main difference? The main difference is just what we discussed. For Euler, assume tau to be 0 because it is inviscid. But for the Navier-Stokes equation, however, we consider the viscous term, okay, meaning that the tau is no longer 0. The shear stress must be taken into account. Okay, all right. So let's have a look. Okay, in the textbooks that I mentioned, or I gave the link before in the class, I think this part is quite essential for students to understand. Okay, basically how the viscous term can be included for the Navier-Stokes derivation. Okay, for the viscous term. Okay, but before we go into detail, need to understand that there's several assumptions that is done by or taken into account for the Navier-Stokes equations. The first one is we assume in the Navier-Stokes derivation, the fluid that we are dealing with is Newtonian. Okay, what does Newtonian means? It basically means the shear stress is um, equals to or is linearly related to the viscous term. So shearing stress is, the shearing stress is linear with the viscosity. Okay, all right. So the first assumption is Newtonian, and the second one we assume that the flow to be incompressible. Okay, I think incompressible means the density is constant. All right. Okay, so this is from the textbook. Okay, what we are going to have a look at is a bit different. Okay, because if you look from the textbook, okay, there is a variable tau. It's lambda. So the lambda here is equals to negative 2 over 3 mu. The viscosity, negative 2 over 3 mu. Mu is the viscosity. Okay, but up until here, it's stated that this term here, the lambda, has not been definitely confirmed until the present day. Okay, so it's still up to debate, it's still subjective. So what we are going to do here, for this derivation, we are not going to use lambda, okay, but we are going to use another term. But the assumptions is the same. We are going to use the assumptions of Newtonian fluid, and we are going to assume the flow is isothermal, means that there is no change in temperature or no temperature change. Okay, because there is no temperature change, we don't need to consider the energy equations. Okay, energy equations is relevant or is valid when we are dealing with temperature change. All right. Okay, so for the Navier-Stokes equations, for the Newtonian fluids, okay, we have a linear relationship between stresses and also the rate of deformation. Okay, so the normal stress sigma xx can be given as negative p plus 2 mu du dx. Okay, so this is how the Stokes, the researcher, the scientist derive and they give meaning or they give the value of sigma xx equals to negative p, the pressure, plus 2 mu du dx. Okay, similarly, for sigma yy, okay, you have negative p plus 2 mu dv dy, and for sigma zz, you have negative p plus 2 mu dw dz. Okay. If we combine all this together, if you add sum up sigma xx, sigma yy, and sigma zz over here, okay, you will end up going to get equals to 3p and then the term of 2 mu dy, or sorry, du, dx, and all the forms of dy and dz. Okay, but it can be simplified by writing these following terms. Okay, remember it should be negative 3p, but if you divide 3 over here, you're going to get 1 over 3 on the left side. Okay, oops. Okay, you get 1 over 3 multiplied by the stress sigma xx plus sigma yy plus sigma zz equals to negative p. Okay, what happens to the rest of the term here? This term, for example. What happened to the rest of the terms? Okay, now for the rest of the term, because we assume it to be incompressible, okay, remember when you sum them up, you're going to get something like this. Sum them up. Xx, yy, zz equals to negative 3p plus 2 mu multiplied by du dx, dv dy, dw dz. Okay, but for incompressible fluids, the vector operator multiplied by v, or basically the gradient of the velocity. Okay, so remember du dx, dv dy, dw dz, this is just a gradient. Okay, a gradient means slope. So for incompressible flow, this is important. For incompressible flow, the gradient of the velocity is equals to 0. So basically you can cross out this term, and that is why you are left with, okay, you move 3 over here to the left, you get 1 over 3. This sigma term in here equals to negative p. Okay, and for the shearing stresses, the researcher has basically came out and derived and is given as the following equation for the shearing stresses. Tau xy equals to tau yx equals to mu du dy plus dv dx, and as given over here for tau yz and tau zy is the same, as well as tau zx and also tau xz. Okay, so now that we have all the stresses in terms of velocity derivative, so we can put these stresses back into the momentum equations in differential form and have everything in terms of velocity. But notice that the stresses that appear in the momentum equations already in derivative. Okay, what does it mean basically? It means when we put the equations above, okay, these equations that we just derived, when we put the equations above in the momentum equations, the velocity will appear as a second derivative. So means second order. So this basically means second order. Okay. All right. So let's have a look. So this is what we just derived based on the assumptions of incompressibility and isothermal. Okay. So the stress term, and this is the momentum equations that we derived before for the Euler. If you remember. Okay. Remember. So we have two sets of equations. Okay, so this is, let's say, A, this is B. So if you substitute back into the momentum equations, okay, what you are going to get is the stress term in the x direction momentum equations as the following. Okay, you are going to get d over dx sigma xx plus d over dy tau yx plus d over dz tau zx. Okay, and this is for the surface forces, and we omit the body force for now. Okay, all right. So where you substitute everything, okay, if you look over here, this is from the momentum equations, the pink box, and the green line, this is where you substitute all that into the momentum equations. The variables or the equations that we got for the A over here for the green line. So when you substitute, you are going to get the following equations. Okay. Then notice when you substitute, you are going to get second derivative over here. Okay, the second order derivative. Okay. So when we rewrite everything, so if you notice over here, we have 2u, so we split this 2u, so we put one u on the left and the other one on the right. So when we rewrite them, we can get negative dp over dx plus mu d square u divided by dx square and d square u divided by dy square plus d square u divided by dz square on the left side, and then plus mu multiplied by the following. Okay, so if you notice here, they involve mixed derivative dy dx, dz dx, so that's called mixed derivative. Okay, when we rewrite again the mixed derivative here into here, okay, you notice that we can bring this mu multiplied by d over dx out, and we are left with this term. But remember, because for incompressible flow, the gradient of the velocity is 0. Remember, gradient of velocity for incompressible flow. Hence, this term is crossed out, 0. So we are left with the only equations on the left side here. Okay. So when we continue, now, so from the F equals to max, the momentum equations before here, all right? So we have the rho multiplied by the term in the bracket here, okay, and which is equals to rho gx, and that's the gravity force, the body force. This is the dp dx, the pressure force. It should be here, the body force, gravity, and then multiply by the terms here. Okay, this is from before. Okay, this is, if I can just show this. Okay. Okay, it's a bit messy. All right, so this is the term that we get before from above, where the only terms equations left from before. Okay, so when we update this in the momentum equations, okay, we are left with this term. Okay, and we write in terms of the vector notation. This is the vector notation. So we are left with rho multiplied by d over dt v plus v dot the vector operator multiplied by v equals to rho g minus vector operator p plus mu vector operator square v, the velocity. So this is the Navier-Stokes equation. Okay, the one that we have over here, this is the Navier-Stokes equations, or the form of a form of Navier-Stokes equations that we are quite familiar with, based on the assumptions that the flow is incompressible, it is isothermal, no change in temperature, and the viscosity is constant. Okay, all right. So just remember, the vector operator square basically means this term here, right? So now we have 3 equations plus 1 continuity equations, which is equals to 4 equations. And for the unknowns, we now have u, v, w, p, and rho. Okay, so 5 unknowns, 4 equations and 5 unknowns. And now we need an equation of state. Okay, this term here, it is non-linear because you have two velocity, okay, two products of velocity, okay, and involves second order PDE. Second order basically because of the derivative, second order derivative. Okay, so the only way to solve this 4 equations and 5 unknown is by using numerical modeling or computational method. All right. Okay, if you look over here, in some of the literature, okay, if you notice, they only include the following terms. for the Navier-Stokes equations. They use sometimes they neglect the G term. Okay, why? Okay, why can G sometimes be neglected? Okay, there are several reasons. One, if the buoyancy force basically due to gravity. So if buoyancy force is not important, okay, then you can neglect G. Okay, when, for example, can you neglect when you're dealing with a pipe flow problem, okay, where the effects of G is quite insignificant, it's quite low in relation to other factors. Okay, pipe, remember, is quite, the diameter is small, okay, so the effect or the impact of the gravity force is quite low. Second one, when we're dealing with a boundary layer problem, or when the boundary layer is quite thin, hence the volume or the mass of the fluid is small compared to the volume or the mass of the fluid in motion outside the boundary layer. Okay. Okay, remember, when you're dealing with the boundary layer, if the boundary layer is thin over here, okay, we can neglect that because the mass of the flow outside the boundary layer is larger than the mass of the mass of the fluid in the boundary layer region. And finally, when all other forces are more prominent or dominant, such as inertial forces, convective forces, viscosity, pressure, and so on. Okay. Okay. So we are not going to cover the energy equations because the Navier-Stokes equations that we arrived before, that's the commonly used Navier-Stokes equations. Energy equations is important when we're dealing with something that is related to the kinetic as well as the all other energies that is moving in the fluid. Okay, but we are not to cover that. Okay. So for the conclusion, we look at the derivation of Euler, which we assume the flow to be inviscid. Hence, we can cross out the shear stresses. For the Navier-Stokes, we take into account the viscosity term. Okay, so that's the main difference between Euler and the Navier-Stokes equations. Okay, so I think that's the end of the differential analysis of fluid flow. Okay, so basically we have covered the first CO, okay, and also the 3CO, which is ongoing. And hopefully we can have a look at some example problems later. All right, so thank you everyone for your time.